All right. Welcome back, everybody, and also welcome our new attendees. For those who missed the wonderful first half, I'm going to be your host for the second half, the hands-on tutorial. So my name is John, and maybe we can go back to the first slide of this event. So for those who attended our first half of the workshop session, you're probably very curious because we made a lot of promise of exciting ideas. It's now put this real thing to test. So keep in mind, this is really a product in development. So this is kind of really illustration. And then we're going to try to walk you through in a few key components, including logging into our system, some major components that we mentioned, including the query builder, the graphical interface, the research asset commons, and some more in-depth examples introduction of the fellows, which solves a scalability problem in big data analysis. So before you get lost, I think I'd like to reintroduce, before I do that, actually, I'd like to acknowledge Microsoft Research, who unfortunately cannot make it here today because it's Labor Day. But they provided the particular data set everyone here will be accessing. And this is an open data. The only condition by using it is cite their paper. So you can do whatever you want with this data. So that's what everybody will be working on today. And they also provided a sponsorship to some of our fellows. To give you some URLs, you can get our website, cadre.edu, which I showed a little bit earlier. I can show it again here. And also the website for our tutorial right here. And there's a link to the Git repo, which posted all our code that we'll be using here. Most of them are in notebook format. And the data will be delivered through our CADRE platform. So if you follow along, you'll be able to reproduce some amazing realizations. So before we get you lost, I'll reintroduce our IT director, one of the project co-director, well, Penchif, to reintroduce CADRE for some of those who actually might miss the first half.
Thank you, Sharon. I see most of you are familiar faces already because we were here for the demo. So I'll try to be a little bit quicker this time, introducing the project. This is the program directorship or the leadership. We are led by Jamie, followed by Patricia Maybrick, who is here with us. I'm in the middle, Sharon Young, and we also have Rob Van Rennes from the Big Ten Academic Alliance, who is also not with us here today. We want to acknowledge all the libraries and institutions who are supporting us. These are the Big Ten, along with Clarabet, which just renamed themselves to the Web of Science Group, Microsoft Academic Research, and the new home for Pat and Maybrick Health Partners. CADRE was founded as a project because of a dilemma we've heard from the librarians that there is no way to provide sustainable standardized access to large and complex data sets as well as proprietary data sets. It's usually cost prohibitive for people to develop it on their own, and for small universities and colleges, it's absolutely impossible. Also, many researchers are not well versed in all the computer technologies required to run their own lab. That's why one major part of CADRE that you'll see today presented by Matthew Hutchinson is the graphical web interface. CADRE is the solution. We offer secure access to library assets, and based on a federated authentication system, we can see the institution you're a part of, you can see the licenses you hold, and we can give you access to proprietary data sets or not. Because this is an open demo today, we'll be working with the open data set that we have, Microsoft Academic Graph. Those of you members of the BTAA and those of you who have signed agreements with the Web of Science group, upon login, you'll also be given access to the Web of Science as well. And you'll also be able to see our research asset commons along with the CADRE marketplace, which allows people to share their resources, derive data, queries, algorithms, create teams, manage projects, and so on. A few words about IUNI. Again, I'm part of the IU Network Science Institute. I'm the leader of the technical team there. These are all the folks that are building day and night, slaving over code so you can have a nice database-oriented system in the cloud. It is in the cloud, first because we have the means of doing it. Second, because it's really cool for stuff to be in the cloud. But also because using cloud technologies, we can scale exponentially and without any limits from 1 to more than 1 million people, and also provide this geographically close to you wherever you are in the world. We're trying to identify the needs of the communities. We identified researchers who need access to the raw data and more compute power than everybody else. They usually talk about APIs and notebooks and access to the clusters that we're able to build on the cloud platforms. We're targeting science of science community with access to the databases we built, which are relational databases and also a slew of graph databases with most of the commonly used graph database languages like Cypher, like Gopher, and so on. And we're also creating a web interface that not only helps you build queries, but will also hopefully be able to suggest the right technology. I am going fast for this because, again, more than half of you have already seen those slides. I will be available here till the end of the conference for any questions you might have for the platform or for any of its implementations. We have federated login, we encourage collaboration, and a big part of the research asset commons is the reproducibility, replicability, provenance, and transparency of data. The entire project is open source. There is a free tier, and it will ensure that any data permutation is assigned a globally unique digital identifier that can be then made part of a publication package. Once published, the data can be retraced to its origins, and also all the algorithms and technologies are embedded in a Dockerized image that allows everyone to replicate the same results, as well as use your data with their techniques or use their data with yours. 3 levels of access: the raw data access, which is exactly as the data came with some augmentation and containerization, and allowing you to use everything that we have access to on the cloud platforms. As mentioned, fill-out database access to relational databases and some graph ones as well. And we have a web interface that will help you build queries to target data. This is the platform itself. I won't go again through its parts. I will leave my colleagues to do this. We can start with Matthew Hutchinson, the data manager at the Indiana University Network Science Institute, who will guide you through the login process and will start the first demo of the web query interface.
Hello, everybody. So as Val said, my name is Matt Hutchinson. I'm one of the developers at IU Network Science Institute, part of Val's team, building the new CADRE platform. And, again, the browser. Yeah, certainly. Let me just open up. Of course, this is Val's computer we're using today, so it only has Opera installed. So give me a minute. I'm not sure who uses Opera these days, apart from Val. But how do I open a, do we have a private browsing window option in? Go over here. There we go. Okay, just so we don't authenticate with Val's ID or anything. So I'm going to show you, everything I'm going to show you today is going to be an interactive demonstration, so you're free to join in and follow along if you have a laptop with you. So we've heard a lot, I think, so far about really interesting research ideas and a lot of great objectives in reproducibility and replicability work. Now, when we first got this grant, we had, Val and Paddy and Sharon came to us in the IT department and said, we've got this grant, we're going to do this great reproducible, have integrated data sets, it's going to be a fantastic project. And we all nodded and smiled and said, yeah, sounds great. And then after they left, we all got together and said, okay, so how's this going to work? What is it they want us to build? And so what we're going to show you today is the products of a year, about a year of experimentation and development, what we've put together so far. Which will, as I say, is a working demonstration, and will hopefully sort of shows you the trajectory of where we want to go in the future with the CADRE project. So, if you would like to join in, the URL, cadre.iu.edu/. So I think, sorry. /dashboard. So this takes you to our current homepage. As you see, we've got our disclaimer at the top. This is still a work in progress. Now I can log in and authenticate using my university ID. So we have two options. The CI login is we'll use your institutional login, or you can use a Google account. So the idea.
You can stop us anytime. Make sure you follow along.
And Sharon's keen for everybody to join in and share this. Yeah. Yeah, so you'll see here in the blue box, we have CI login. So this is a service for academic institutions to provide a central location for their institutional logons. Although we discovered it doesn't have as wide a coverage of European institutions, unfortunately. So if you don't find your institution there, feel free to use the Google login if you have a Google account. In either case, you should end up in the same place because all the data we'll be using today is the publicly available Microsoft academic graph. If you authenticate via an institution, which is part of our CADRE agreement, then you'll also be able to access the Web of Science data, which I'll be able to show you, so I'm going to use my Indiana authentication. So I'll be able to access both data sets, but we'll only be using the Microsoft data today. This is going to take me to my university login. Give me a moment. Also use two-factor authentication, but this proves it is a real demo. I'm doing it live. Oh, unfortunately, I brought it back up. Let's give me a moment. So this is the CADRE dashboard, CADRE homepage. And you see we have a few different sections here, which we'll go through in more detail. If you are following along, I would ask you to scroll down here to where you see the ISSI data package, hit run, and just run package. I'll circle back around and talk a bit more in detail about what we're doing here with the packages, but this will set up your environment so you can follow the examples that I'm going to be going through today. So I can let that run in the background. So I'm going to start off by querying the data set and extracting some data that I'm going to use in my analysis. So as I mentioned, we have two databases available right now. Most people will be using Microsoft Academic. If you do have access via our service, you can use Web of Science as well. But today we're just going to use Microsoft Academic. So I'll follow the link through to our query builder. And if you are following along and you use this system, you'll notice, you can search for a variety of things, but there are obviously areas where we can improve the complexity of the query builder, and those are features we're working on at the moment. So for my simple query, I'm going to look for all the articles from, try and spell it quick. So I realize I can't talk and type at the same time, so you have to give me a minute while I fill these in. Okay, there's Bill correctly. Okay. Yeah, that's true. Okay, so that's my query I structured. You'll see here the different fields we have available to search. So you can expand this, and so these will be the different potential columns in the exported data file I get from the database. I'm just going to stick with the defaults for now. You can simply click on and toggle on and off the different fields that you're interested in. And then what we have down here are the network queries. So this is still in the very early stages, but by including a citation network, I'm going to include the first generation citations for all of the articles which are being returned by my initial research. So my query won't just return journals from Scientometrics, or articles from Scientometrics and articles from Journal of Infometrics. It'll also return all of those articles which have cited those articles. And in the future, we want to expand this, obviously, and give it more sophisticated network searching. For today, if you are joining in, you'll only be able to do a 1-degree search. We limited it just because we didn't know how many people we would have running queries. But we would like to expand this. In theory, the database has the entire citation network, so we could support as many generations of search as you want, but we could be here all day with the current system that we're building this and expanding on it. So for today, we'll just do 1 degree. So then I can do a quick preview. So this is going to return the first few records for me from my initial search. And hopefully it will be ready any second. Hope you enjoy my logo here. It doesn't make you too be motion sickness or anything watching owls. But, yeah. Oh, okay. Yeah. Sure, yeah, I want to in the background. So we have 2 folders, journals from the Scientometrics and journals from Infometrics. Yeah. Right.
There's no journal.
Oh, no journal of just Infometrics. Okay, well, I can run it again.
You run the data package. You compile the standard data set.
Okay. So there you go. So this is a preview, so I can look at the initial results of my query and decide, do I need to add any fields? Do I need to go back and revisit my query before I run the entire set? So I can start to search through these and make sure this is the output format that I want. So these are all of the, if we think about it in terms of our network query, these are the 0-degree results. So I assume I'm happy with this. We're okay for using Journal of Infometrics. I'm going to submit the query. And so the full query will run asynchronously, so I can check the status of it. You see it run in the background here. And this is, you see the green rectangle here. So this is the initial package that we ran at the beginning to set up the data environment. And right now we're running across the full Microsoft Academic Graph, which I believe is what, 200 million records for searching, or more than that, I think, at the moment. Plus the citations, the first-degree citations for each article. So now that query has been completed. So now I want to see, well, where are the results? So I'm going to go to my Jupyter Notebook up here. And so this is going to take me to my development environment. Now you'll probably see if it's your first time using the system, your notebook is not running. So we'll need to create our notebook server. And so this is going to set up our Jupyter Notebook in the background so we can access the files that we've been generating and start running some analysis and programming against them. Hopefully, yeah. Oh. Oh, right. Yeah, so make sure it's Scientometrics or Journal of Infometrics. Yeah, not and. Right. All right, so now my notebook is up and running. So it's going to take me to my programming environment, I believe. We might be having some network issues today. Things are running a little slowly. Is this a pop-up that's being blocked? Good loading? Yeah. Yeah. Okay, so this is my environment here. Let me take you up a level. You'll probably see something like this. If you run the package initially at the beginning, you should see the packages section. So this will be, whenever you run a package in the CADRE platform, you'll see the information about that package will appear in that directory. ISSI tutorial directory should be automatically populated for everybody, and that's going to contain all the scripts we're going to use in the different demos today. So everybody should be able to access that by default. And as our setup today. And then queries results is where our database is going to export the results, the CSVs that are generated by any of the searches that you're doing on the system. And this file in my section is just a backup of some of the data we've got, so I had another copy of it. So you should see in the query results. There we go. So you see there's a few different queries I've been running and preparing for today and trying out different things. But these are the ones I've run just now. I can open these up. Make sure you there's nothing secret going on here. So this is the output from our initial search on the database. So you see these are the fields we selected from the graphical interface. And at the same time, we have these two additional files which are created. So these are the nodes. So these are all of the records from that initial search, plus all of the first generation citations. So this is the output of our network query here. And you see, this is again limited to the same fields that we had when we chose which fields we want to output. And the edges file is a simple edge list of ID to ID. So we can reconstruct that citation network resulting from our queries. This is how we output citation queries at the moment. We're open to suggestions, but for now we're thinking in terms of tables and CSV files. But we've considered JSON and more complex structures as well that may come in the future. So again, if you're following along, if you go to the ISSI tutorial page, you'll see a file called demo_01, and that's the file we're going to run now. So this is my Python programming environment, and this is going to run against the output of the query that we just ran. So there's a couple of file paths you'll see here. So if you run that initial package at the beginning that I mentioned, you won't need to change anything in this script. You can just run it as is because the data is already included in that package, and that's the name from that version. You can rename these CSVs, by the way. You don't have to memorize these long strings. And just for today, I didn't want to mess around typing out different names and files and things. But then if you want to actually write your, if you want to use the actual results from the query you just ran, rather than the pre-built query the package generated, then you can change this, uncomment this line and change it here. See, this is the query results folder, and this is the CSV generated by the search. And so just, again, you can verify that I'm not just hiding something here in the packages. We are using the actual data. So hopefully we can run this. I run this one. You see, now we have the results of our initial search in our programming environment. So for my demo, I'm just going to look at that degree 0 file, so just those searches. I'm not going to look at the network component. I'm going to leave that to Felipe. He's going to come up next and do some more complex network analysis. But here we've read the 0 degree file, put it into our programming environment. Then I have a whole bunch of, you can see I've already got the result here. I'm going to do some data manipulation. I'm going to filter it down to the publications, the articles from those two publications, and just aggregate them, both the time span that the data covers. And hopefully down the bottom here, we'll see a nice plot. And run it again just to make sure, just to show you it really is being generated. There you go. And so then you see over time the combined publications and all of the general informametrics and scientometrics. Now, obviously the goal here is not to impress you with my amazing Python programming and this fantastic insight. I've discovered that there are more publications over time, but rather just to illustrate the potential workflow for a researcher that they can find data they need from the data set and then begin to analyze it, create visualizations, start programming against it, all within our platform. They don't need to export the data. They don't need to set up anything locally or install anything locally. They can do everything through the web browser, and we can be sure that they're only working on accessing data that they have permissions to access. So the open data, if there's any restricted or proprietary data, they won't be able to query against it and bring it into the environment like this. So I'm going to talk a little bit about a future feature, which we don't have on here right now. But what we want to be able to do, or what we will be able to do very soon, assuming I'm a researcher and I've run my queries, got my data, produced my analysis and research that I'm like, I want to be able to share it with others, we'll have a button on here which will be to save my results and my analysis as a package and then share it in the what we're calling the research asset commons, so within the CADRE environment. So I can go back to the home page and show you some of those. I'm going to go to the marketplace. So you see here we have some sample packages, including the one that we ran at the beginning. And so you can imagine that these packages are the outputs of work people have done on the platform, and they've decided they want to share them with the community. And so they will obviously include more information, author information. And we also want to start assigning DOIs to these packages so they can be cited in people's work, and they can be searched by DOI as well. So I'm going to pretend now, I'm going to run one of these and show you how it might work. Which, let me make sure I get the right one. Okay, so I showed you how I would share my research. I develop my pipeline and share it in the marketplace. So now I'm going to pretend, well, I've been reading some work. I've been reading one of Felipe's papers, and in the bottom of the paper, he cited some of the analysis he's done has been published on the CADRE platform. And I want to make sure, for some reason, I don't believe him. I want to trust him. I want to recreate his results, so I want to investigate more about it. So I find the DOI, I go to the marketplace, search for the DOI or search for Felipe's name, find all the packages he's created, and find the one that he cited in this article, which is the figure package, correct? Make sure I get the right one. Which one? Yeah, this one? Yeah, okay. Make sure I run the right one. I don't want to mess up your demo, I know you're going to talk more about it. Okay. Okay. All right. So from here, I can run the package as Felipe authored it. So I can just repeat the same code that he has done and have it run, and then that'll bring everything that he published into my programming environment. So I can look at it. So you see Felipe's package is completed here. So I'll go back to my notebook, which I already have open. And I should be able to find it in my packages. And here we have the XNet2 figure package. And output files, right? And the figure PDF. And so then this is going to open up the output, which I've just recreated from Felipe's analysis. There we go. It says network visualization. And so now I have everything, all the data, all of the code that went into generating this visualization, I now have in my programming environment, so I can study it, take it apart, look at it, and verify that I can get the same results as Felipe did. And I think now I'm going to hand things over to Felipe himself, who is going to show us how to dig into these packages and how they get put together. Oh, you want to start this? Sure.
Thank you.
Things I missed. Thank you.
No, you missed nothing. It was fantastic. Thank you. I just want to tell everyone that this is a very early stage project. We are still in the proof of concept. So what you see are working prototypes of what is about to come. For those of you who think this is too complicated and too technical, everything that mentioned in the Python notebook will be available through the graphical interface soon. You can also stop at the first stage when the queries generate the edge and network list, all the table itself, and process it in any other tool you want. A second note to make is that we've been emphasizing how these packages help reproducibility, but they will also be soon packaging tools that you can use on the data. And for those of you who think this is not technical enough, we'll continue with Felipe and Shaoran will at the end hand you over to a Spark cluster that is being created dynamically so you can process all of your data.
Anyone has questions?
Yes, if anyone has questions, now we can
follow.
And once you check it now, around there, what you want it is. Or you can take what Sharon did and modify aspects of it, and then run the next update that to something similar, but a little bit different.
Yes. So here we showed you the package and the result, but if you go inside the package, you can find the actual source code to run it yourself. And soon the package will be able to be extended with your source code or with your input data. So here is the actual code that generated the picture.
Just did a complicated thing.
Yes, feel free to exercise with it, change the color, change the topic, change the title, you will create a different result.
Thank you everyone for coming. I am Felipe Silva, and I am research scientist at IUNI. Here I will show like some practical approach. How can you use this data in a simple way so like you can have some results from it and maybe things that you can publish later in a paper, or you could just start getting insights. So I just show how powerful this environment can become. So I will start from Mateus notebook. So in fact, I have another notebook for demos. So you can go to ISSI tutorial again for those that are following, and go to demo 2. Okay. And from here you see another notebook with some code, and I will go through this code, and I will show you a way to get to work with the networks in this environment. So a way to do that is loading data. So I'm just going first to repeat one process that may be needed. So first thing, you need to go back to the marketplace and make sure that you run ISSI data package so that all your data is prepared for what's I'm going to show. And the second thing I would like to show here, not that I am here, is that there may also be packages that are just for pre-processing data. So they may not be necessarily applied to like generate figures, generate like final tables, but to like pre-process data in the same fashion as, for instance, Sharon may have used it on his paper, or another one maybe using his paper. So I will just show it. This is the second one. This is Square to XNet. What this does is it simply generates a network from all the input data that all the query data that was obtained from the queries that you can do using the interface. So you just run it. It takes some seconds, I believe. A bit more. Okay, done. So from here now, you can go back to your environment, to the Jupyter environment, and you see that in the packages folder, you can, okay, take some time. Okay. You can see now another folder there, that's query to XNet, that contains the results of the package that I just ran.
Because delivering data is taking time.
Yeah, maybe. So as you can see, there's now a new file here. This is just a format. You could use any format that you like for networks, but this is just a specific format that we are using. So it contains like the edge list and some data as well. So if you can visualize it like. So, and there is another thing that this package does. It calculates K-core. That's just a way to say that some nodes are more in the center of the network. It's not exactly like that, but we can say something like that. And this also calculates community. So it detects community, the community structure in such a network. And for those that doesn't know, the community structure is just it's just like an organization of a network in which like you may have nodes that are connecting among inside a group that are more connected inside a group than connected to outside to nodes that are outside the group. So just some kind of groups that are tight connected in a network. Sorry. Sure. Let me go back to. So you go to the marketplace first. So you need to go back. Okay. Okay. So you run the package. Okay. It's already done. It's already there. But Yeah, but if you want to see the results, they are in the root. So you need to click here in the root folder.
Yeah.
And then package. Okay. And then prior to XNet, this is just doesn't have.
Have you gone?
Okay. So it should be here. And then, as well said, you can also have access to the code itself that generates that particular network. In future, we plan, of course, to have parameters, sets of parameters. You can change input data. You can change even the code and maybe make a new package or some kind of variable. So that's idea we have for the following. So let me go back to again to the package, and we can see here there's a lot of packages here, 6 packages here, and there's another one that's XNet Word Cloud. So what this does is it takes the network as input, and it reads out the I believe the titles of each journal of each publication there, and just simply build a figure containing the word cloud for that. So I just run it, and I can go back to package again, and then word cloud, XNet word cloud, output files, and as you see, there will be a new file here containing like the word cloud. So this can be very useful if you just need to, it's taking a while to boot. Okay, so this can be useful if you just need to like get an overview of an area, something like that. So you can have this kind of package done. You just click and run. And this is like informatics and symptomatic journals. So that's why you see this kind of patterns. Of course, you could apply this for other data. Let me just close some tabs here. Okay. Now let me go back again. So Matthew already showed you the visualization package. I'm not going through this again, but if you see the resulting, if you see the resulting figure, it's a network. This is the visualization. This was generated by visualization package, and it contains the network itself, of course, but it tells the colors indicate your communities. So this may not visualization with communities there. First, you would like to have a more in-depth understanding of these communities. And the way to do that, the easy way that we already have something, is just create word clouds for each community. And we also have a package for that. This is, sorry, let me show you. This is an XNet to communities word cloud package. So it's a little bit more complicated because it generates word clouds for each community in the network, but when it runs, it's very simple. So let me go back to package. I believe it's already done. Okay, so you see this folder here, communities word cloud, output files, and now there should be. Take some time. Yeah. So there is now the top 4, the word clouds for the top 4 largest communities in this network. So I don't remember exactly how to do. Yeah. So the colors match which communities with. So you can. I'm not sure. Okay, not sure how to zoom out this. So you can see like, you can try to understand which community means here. So like, this may be like journal impact factor, citation, things like that. And then you have a community more dedicated to developing or understanding indices. There's another for collaboration networks that's here. you can get a better understanding of a network with a simple pipeline. You just press some buttons and have something. So this is very good if you are not like a programmer, if you are not a developer. And the idea of CADRE is to also have this audience and let them have access to this kind of advanced tools, but in a simple fashion. So packages would provide this kind of environment for you. So let me go back now to the notebook environment. So if you now let's say that you are now you know how to program, you are like a researcher, or you are working on, you need to like do something more sophisticated, or do something more different, or do your research here. So the notebook may be a good environment for you, because it allows you to, let me just increase, okay. So you can now, from the notebook, you can now process your data, and as Matthew showed, you can load the data and process it using Python or whatever language you prefer that is compatible with Jupyter. So let me run this, and I will show you what this is about. You saw that packages I run, and I will try to reproduce them now using the notebook. So we have now a more interactive way to do that. And this is just the important things, importing some libraries. And here we can now load the network from a specific file we have. And you can uncomment this part if you want to use your own data. So this will be available through GitHub. So you can later on try it yourself. Or now you can try, but so this will show some statistics of the network, such as number of branches, number of edges, average degree, things like that. Very simple thing. But then you can also, what this does, it loads the network that you just generated through the package or by a query. From that, it generates an iGraph network inside Python. So if you know iGraph, you can use iGraph, and you can use all the power of iGraph here. Of course, if you prefer NetworkX or another library, you can use it. You just need to prepare your data and process it accordingly. And now I need to just demonstrate that you can also obtain in a more interactive fashion the word cloud. So here it's using paper abstracts. It takes some time, yeah. So it's done, but of course you can, because it's interactive, so you can go here and just use another property. So let's see, we have here has a property of network original title. So instead of using the paper abstracts, we could use the original title. And take some time again, but now we have the same word cloud, but now for just considering the titles. Here you can obtain a network properties, like here in calculating the K-core. It may be useful for filtering network, things like that. And this also shows the time span of the network, so you can get properties from that. It's very easy to do. You can get the giant components of the network, so that it's a very easy way. And here we have like, if you compare to the older numbers, we started from a network with almost 7,000 nodes, and now we have about 6,000 nodes by obtaining just the giant connected components. And you can also obtain communities here, so you can obtain the community structure. So for instance, there's 18 communities for this network. I am using the Loven method here. It's not really appropriate for this kind of data because citation data has direction. But here we are going to like a very simple way to do that, so don't need to think about that right now. Still, we have some kind of communities, and we can also save the network somewhere. So this is just an example of saving the network. And finally, we can also filter the network. So in fact, every result I showed before was for the network obtained considering articles after 2000. So let's go later to the details of this code. But now we have a very much smaller network that's only it's less than 2,000 nodes. And finally, we would like to have the visualization for that. So this is all being generated in real time. So we now have we also have a code for generating the visualization. It takes a little bit a while, but it generates it. And of course, the positions may change because this algorithm is non-determinist. So of course, you can set if you would really like to go in a reproducibility direction. Of course, you need to set your seed, your random seed, to some fixed value, so everyone always get the same results. But it's still a way to go if you have similar figures. And then finally, this code generates. No, this is just some codes that are needed to generate the word cloud, and it takes a while as well. But it also generates the word cloud. So we can reproduce everything that we see in the package environment here, but here you have more control over everything. So you can like change things, change the code, and do that interactively. Now, let me go to another level. So this kind of analysis can also be, it takes some time for go back. So if you go to ISSI tutorial again, folder, and open demo tree, you see another set of codes. And here, this is really a prototype now, so it's work in progress. So it is just to show you the power of this kind of environment. And what we are going to do is that this kind of technology, web, cloud, things like that, also, when you mix them together, they can become very powerful, because you can do anything that you can do on a web page. You can now bring this interactive thing, interactive way of dealing with data to the notebook, and even publish it elsewhere to like your website, something like that. So what I'm going to show you is an example of interactive visualization for that network. So you can run, if those that are following, just open demo tree and just run this in a sequence. So run the first and the second. This just loads the network again. And here there is a more complicated code that I'm not going into details, but it just generates time evolving network of what you have. So it depends on your browser. So this is being run inside your browser. So you can run this cell here, and it may take some time to run or not. Okay, it's done, but it takes some time to show up. And maybe, yeah, take some time. Okay, now it's, because we have an interactive, so you see a network here, but we don't have a run for showing it entirely. So let me just reduce a little bit the size of it. So because it's interactive, you can do that and just run it again. So let's see if this is enough. Okay, it takes a while to load the data. Of course, it's coming from US, so a little bit. Okay, now we have the network, and let's see if we can. Yeah. So you can see the network here, and it works like any. How do I get? So the document mode. Yeah, maybe I can gain some pixels here. Okay. So here you have an interactive visualization of the network, and this is the network of 1994. And because it's interactive, you can go over time, so you can see how it evolves over time, and it's interactive, and it runs inside your browser, so it's a very powerful way to do that. Of course, it depends on your personal resources, but of course, this kind of thing can be at some time be done on the cloud as well. So we need to figure out a way to do that yet, but that can be done. But this on modern computers, it runs just fine. So you don't need to have like a much more resource to visualize this kind of thing. And from this you can do like you can go to a specific time frame and see. You are not seeing that, but you can see like the title here. So you have some interactivity, and this is like this kind of code can be modified to your needs. So you can see other kind of features from that. And no, I just use a gesture here. So. Just to show you that this is interactive, I don't have it here. Yeah, maybe I can. Let me just change the time frame. So. Okay, so instead of going beyond 2000, let's go up to 2000. So let's say we may not see much. Okay, let's see from the 8 to 2000, just to show that we can like okay. So this is a much smaller network, of course. It's surprising centered on a particular article. Let's see which one is that. Okay, quantitative studies of science accuracy by bibliography. So yeah, and then you can. So this kind of thing can be done for any kind of network that you generate from a query, and from the query you generate the network. From the network you generate visualization and interactive visualization, and so on. And here you just show, just reduce the size for that. Okay. And another thing that we may be planning is to improve this kind of visualization. So it can become like, we could see like the entire network, for instance, in 3D or in other kind of things. So from that, we can also, we can have access to a way to visualize networks that's more powerful and can be used to see like very large networks. For instance, this is the entire network. Instead of limiting to a certain time frame, we can see the entire thing as a whole. So, and of course, you can also change parameters here, change the size of things, and you can see you can experience and explore those networks. Anyway, so that's something that we have in mind. We keep in mind when we'll be developing the platform. So that's the final thing. So maybe is it questions now or no? It goes to Sharon, right? Yeah. So let Sharon go.
If you have the questions, we are happy to help you with pen by hand. This is really amazing work that Unity has generated. This particular data like preparation is right? So they are secretly using your own laptop's GPU.
Yeah.
So he's hacking the system already. That's previously unreasonable to visualize that at this size at a notebook. It's impossible basically. If you use any visualization tools, that's at this size will basically slow down your machine significantly. Now it's running on a notebook environment. So this is the power of the container that we built. The backend. I think in the second part of this demo, I'm going to give you a little more idea of the technical details. I'll keep it at a high level that make all of this possible. And we'll actually go in depth with a technical problem that one of the fellows faced, Yuko, and illustrate how we help him solve some of the scalability problems, as well as our preliminary demonstration of how a reproducible environment can be created, assuming you have a ready to go GitHub repo. So let's get back to the slides. So yeah, let's before I move on, I just really want to make sure everybody has their question answered at this point. Any questions so far?
Great. Let me just say that the feedback is so important. When people start to get their hands dirty on what they see that can be improved, or what they see that, or what they really like, tell us.
That's a great point. So I should give guys means a channel of communication to give us feedback. And if you have any comments, I think if you go to our website, there's a contact us form. You can fill out if you have any thoughts, what kind of features you think is desirable. Also, we have a continued process of user story collection, which we started back then in the last year, I think, which I think you can get from Work With Us. And let's see. It's not here. Let me see. Fellowship programs. No, there's actually a maybe it's here. Yeah, there's a user story form. If you click on it, some of you might actually done it already. So you can. It's very simple. Just plain English, explain what you want to do as a researcher on our platform. And these will go into our developer cycle and our agile develop mode, literally read from the system and consider implementing them into our platform seriously. So now let's go back to the slides. So I'll be quick here because I see a lot of you also seen this part before. So I just want to reintroduce some of the work that our fellows planning to do. Maybe some of them already did on our project. And we announced the fellowship program earlier this year, and now we have 7 of them working with us. And a lot of the features we see today actually was based on some of their feedbacks. And we were looking forward to continued collaboration into next year and longer future. '17, yes. So as you can see, so as these early adopters, we collaborate them closely. They also help us, give us, feedbacks. We also have a little community based around our Slack channels, GitHub repos, and Twitter accounts. And in return for their testing, we offer them free cloud credits essentially. So all of these features you saw run in our AWS servers, and they can access now without any charges. And some of them are getting travel support to attend this event. So out of the 17, some of them unfortunately didn't have the opportunity to present. Representing the team from for Georgia University, I think it's Michael Witt, who's here with us today. They're planning to connect Web of Science and Lab Graph with data citation, which is a data set focused on research data itself rather than metadata. So you will see a trend is connecting different data sets is a big thing that we encourage, because that's a lot of value once the data are connected, and they serve as valuable resources so other members of the community can build on top of. Representing the team from Michigan State University, I think it's Scout, who's joining us today here. They plan to use the data set from CADRE to investigate how sustained development goals, sponsored by United Nations, are affecting collaborative research across the globe. And this is a cross-continental collaboration team with Scotty Warner, Adam Flosi, and myself actually. And Adam is presenting a talk on Thursday about our early preliminary to this project, but now we plan to expand this geo-coded study of how transportation affects collaborations to the much bigger data sets. So if you're here with us today earlier in the workshop, Michael Park from Minnesota presented their plan. As they say, they have a big team, big plans. Not just modeling different dynamics of scientific disciplines. They also wanted to contribute cost distribution algorithms to the platform. And Samuel Hansen, the star of our previous event, actually presenting two separate projects. He's just too good for us to reject any single one of those. And he's studying very fascinating patterns of how mathematical discipline and in conjunction with mathematical biologists as well, how these different journals in different disciplines have very different patterns of bibliographic data. So if you have any questions with these fellows, just feel free to talk with them, and I'm pretty sure they're very happy to share their experience. So last but not least is the project who actually presented twice today, and this time I think it will be Yibu presenting for the team from Indiana University. So they have been sort of the earliest group we've been collaborating with. That's why I think they're the furthest along, because we are co-located in Indiana. So he's going to actually, Chao Ming presented some background of their research. But I think Yibu instead going to focus a little bit more on technical details and how we collaborate.
Hey guys, this is Yibu. I'm currently a PhD candidate in informatics at School of Informatics, Computing and Engineering at Indiana University, Bloomington. Today I will present a more technical introduction on one of my research to explore eco-centered citation networks. So in bibliometrics and scientometrics, understanding citation impact is very important in this field. And the scientific impact is actually one type of impact among all kinds of impacts, such as economic impact, technological impact, and society-related impact. And among all types of scientific impact, citation impact is one type. And in my research, I'm trying to understand the citation impact of scientific publications. That means the scientific impact received from the perspective of citations. So there are several benefits of understanding citation impacts. First of all, from an empirical perspective, measuring citation impact offers a useful way of examining the scientific impact of publication. This is mainly from a research assessment perspective. from a more generous aspect, measuring citation impact can also assist us in understanding knowledge diffusion, knowledge dissemination, and the use of information, especially from the metrics, scientometric, and infometric perspectives. There are several ways previously to understand citation impact. First of all, some bibliometricians use count-based strategies, such as raw citation count, or normalized citation measurements, such as normalized raw citation count based on the paper's published year or the paper's domains. For instance, we cannot compare a biological paper with a mathematical paper, right? And the other ways of measuring citation impact is the network-based strategies, considering the whole citation networks. For instance, famous PageRank algorithms and agent factors, both of them considers the whole citation network into consideration. However, these network-based measurements need some local details. For instance, here we can show both of the publications A and B receive 5 citations, namely A1 to A5 and B1 to B5. However, their citation impact should be different. For instance, the second figure, we should find the citation impact of publication B is more wide, such as a true paper, and most of the citing papers just cite the focal publication separately without any interaction. When I say interaction, it means citing relationship. On the other hand, for publication A, it receives 5 citations, but all of these 5 citations cite each other, such as A5 cites A4, A4 cites A3, something like that. So the citation impact of publication A are considered as more like deeper. Here's another example. I use one case, which is the H-index paper published in PNAS in the year of 2005. And I consider the direct citations between citing publications. For instance, let's say A is the H-index paper, and there are some citations between citing publications, such as from B5 to B4. That is not direct cited to A, but from one citing publication to another citing publication. So I examine the domains of the citing and the cited publications of H-index paper, and I find that most such relationships are in the field of SSH, which means social science and humanities. Okay, so these are the 5 domains I consider. Like SSH is social science and humanities, and BHF is the biomedicine and health science, and PSC is the physical science and engineering, LES is the life science, life and earth science, and MCS is mathematics and computer science. And in the right table, we can find the published year and discipline distributions of the citing publication of H-index articles. Direct citations between citing publications, so it's kind of complicated. So in the second table, we can find in some early years, like 2006 and 2007, most of the citing publications are from the social science and humanities domains. But later, after 2010, the impact of H-index paper expands to more general disciplines such as earth science and computer science and physical science and engineering. So these 2 tables help us understand how an article impacts our research and how the patterns are. To this end, we propose the ego-centered citation network as a tool to understand citation impact. In the right figure, we can see a focal publication A and its citing publications, as well as all of the citing relationships between these citing publications. So here we can see there are 2 types of citations. One is the dotted line, one is the solid line. While the solid line is the relationship from citing paper to the focal paper, and the dotted line is the citing relationship between citing publications. So there are 2 preliminary research questions. The first one, do direct citations between citing publications occur frequently in all disciplines? Secondly, how does the direct citations between citing publications differ in papers with different citation impacts and in different years? So this is more like a bibliometric analysis from the perspective of direct citation between citing publications. So here are some preliminary results. In the left figure, the x-axis is the number of citations for publications, while the y-axis is a percentage of papers with at least one BCCP. That means in the middle figure, if a paper A has at least one dotted line, we'll just count it in the left figure. For instance, in the left figure, we can find for papers with 10 citations, there are 85% of papers have at least one dotted line in the ego-centered citation network. And in the right figure, we can find that such patterns increases with more citation. For instance, the right box is the high impact paper, and the middle box is the medium impact paper, while the left box is the low impact paper. We can find the median of the number of indirect citations increases, which is the orange line in the middle of the box. And this figure shows that such pattern doesn't change over years. For instance, regardless of high impact paper, medium impact paper, and low impact paper, such pattern doesn't change over years. Like paper published in the 1960s, 1980s, 1990s, and 2000, such pattern doesn't change. So since this is an introduction in terms of more technical, so here I would like to show more technical details of how to extract citing relationships from the raw and entry tables. As we know, the Microsoft Academic Graph in CADRE is stored in a post-array table previously. And firstly, I wrote a Python script to extract all of the citing relationships into a TXT file. To this end, I need to import some a package and run the SQL query, and then for all of the results from this select sentence, I store it in the TXT file. So to this end, I use one package from collections import default bit. That is because if I run the sentence, like the if paper in a dictionary keys, that will take very long time to extract, to examine whether a specific value is in the Python dictionary. To this end, I just use the from collections import default bit. If I use that package, then I will not use to examine whether a specific value has existed in the dictionary, in the Python dictionary. To use that, I just use the old one, which is paper citing, is defined as the new default bit. So essentially, it's a list. So in my research, there are several difficulties. The first difficulty is how to extract direct citation between citing publications. So in this figure, the relationship from B to A is a direct citation, which is very easy to extract. But the dotted line, which are the direct citations between citing publications from the perspective of A, is very hard to extract. So my sample output should be containing 3 columns. The first column should be the ID of focal publication, such as A, and the second column is ID of B type paper, such as the citing publication like this, connect a citing publication and a focal publication. But the third column should be the citing publication like C, like this type of citing publication, cite another citing publication, but also the focal publication. So I hope to have an output like this, containing 3 columns. This task is actually computationally expensive, very computationally expensive. So here in MEG, we have around 0.1 billion papers. And previously, I tried this Python script. Actually, this Python script can help me to finish this task. However, that will take forever. Okay, let's look at this Python script. It's very simple. So first, the first line, I define a default bit, which is a Python dictionary-like data structure called indirect citation. The key of this directory is the ID of the focal publication. And the value of this dictionary contains a lot of lists, Python lists. And each list contains an indirect citation relationship. To this end, I need to have two loops. For paper in citing year.keys, that is to examine whether this paper is contained in a specific like publication year information. And then I have two loops. For citing paper 1 in paper citing paper, for citing paper 2 in paper citing paper. This is to examine whether a specific indirect citations really exist in our MAG dataset. And then if we really find such relationship, we'll append this new list into this default peak. So this is quite simple. However, it will take forever. This is the first difficulty, to extract DCCP. The second difficulty is I'm interested in the self-citations in ego-centered citation networks. Here, we define self-citation as like if two papers share at least one author and B cites A, and then we will define such citing relationship as a self-citation. However, such self-citation is the first order citation, which is not quite difficult to extract. But what I'm really interested in is the second order self-citations and the third order self-citations. For instance, in this circumstance, the first one, A and B don't share co-authors, but A and C share co-author and B and C share co-author. We call this a second order self-citations. For instance, we two are co-authors, and he cites one of my papers, so this is the first order citations. And if we two are not co-authors, and we two are not co-authors, but they two are co-authors, that is a second order self-citation. And we are interested in whether your knowledge accumulation process will impact the self-citation process. But that is not the most difficult thing. The most difficult thing is the three-order self-citation, which is, more, we need to examine the shortest paths in the citation network and the quality network. For instance, in the second part, we will find A and B don't share co-authors. A and C share co-author, B and D share co-authors, and C and D share co-authors. That will become very complicated. And this indicates how researchers' social distance impacts on their self-citation patterns. And I'm interested in how to technically achieve this. Okay, so now we have two difficulties. One is the self-citation in ego-centered network. One is how to extract direct citation between citing publications. In terms of the second difficulties, we need to know the shortest path and the length in the coalition and citation networks. That means in this case we have two networks, and we need to calculate the length of the shortest path. And such networks are quite huge. And now let's invite Sean to come here to detail how to solve these two difficulties.
Well, you just throw the hot feelings in my hands. And first of all, I cannot promise anything about the second challenge, because before you can do anything with your self-citation, we need also certification first. And for that, we are waiting for our help from the University of Michigan guys, please. So today I'm just going to try to tackle his first challenge, which I think we successfully solved, and in the process illustrate how flexible our computing environment can be when dealing with data at this scale. So basically, I will cover scalability in our platform first. So just to remind you what the first challenge is, which is the simpler of the two. So the key challenge is when you actually want to build beyond the first degree of neighbors. In this case, you want citations beyond unique neighbors. In traditional relational setting, a table join is mandatory. And
they will join at this scale, which is, billions of edges, hundreds of millions of nodes, is not feasible. They will not fit in the memory of traditional, conventional machines, and they will take forever. And some of our users, our previous enclave installations, has experienced this firsthand. Some of the queries runs for weeks, and that's a fundamental challenge, and we are really trying to tackle on this when we design CADRE. So CADRE solution, so beyond the easy-to-use graphical interface we saw earlier, is really a unified search engine, if you will, with optimized combination of different types of database technologies. So we are considering relational, graph, document databases. Each of them has strengths and weaknesses. When combined for appropriate purposes, we hope to achieve better performance. In this case, I think we already achieved orders of magnitude improvement compared to our, pretty terrible installation previously. But we are just in the starting stage. We have a group of database experts working with us who's going to be benchmarking a list of state-of-the-art database engines. And we will implement the appropriate choice once we've done it. So this is the promise land once we've done it. You'll be able to search data at this scale effortlessly using our interface you saw earlier. So we're not there yet, but I think we can achieve that. And to do that, as some of the components you already seen earlier today, like the interface and the notebook, and which is as a comment I can mention later for reproducibility purposes. But for the scalability, it's really the databases that I've been talking previously. And give you some very high idea of why different databases install different type of queries. So the following slide is from one of the top commercial graph database CADRE brands. And so basically, this is the figure I was referring to. The join of relational tables becomes a bottleneck when you have a huge data set. But if you're looking for something like citations, relationships, a graph database is a much better optimized model for that kind of query. So in those databases, you store your neighbors directly without going looking huge join table, and that consolidates speeding up. And guess what? You guys already used that already in earlier presentation, if you have been following along. So in our interface, if I can go back there, which is the other one. Okay, so when you go to query interface, behind the scenes, I guess I have to log in again. I'm looking at my Google account. I guess just to showcase, if you don't have the CI logon account associated with it, you can also access through this means. Okay, there we go. So currently, the filter, text-based filter search is implemented by traditional relational database, but the graph query, as you can see here, is already running with a Neo4j database. So that's why we're able to extract pretty quickly. So it's in like 12 seconds, 13 seconds of a first order neighborhood of 6,000 papers. So that's already a quick improvement if you have tried something similar in a relational database. So if we know because we expect a much bigger crowd here, we should enable a second order query there, because they usually takes about a couple minutes when optimized. We're afraid because it will wait, if some algorithm keeps running second order, it will slow the whole system down, so we prevent it from here. No worries. my demo. So go back to my slides. So before we go to the demo, just want to quickly give you some, candidates we're considering. So top consideration besides being native ground databases to support this kind of relational search is if they support distributed distributed computation. So far, Neo4j is only running on single node. So we're really considering switching to something like typograph or GenSgraph, which can run on classical computers. So with that, we hope we will be able to deliver beyond even second order queries at a much faster speed. So this is really progress we are making at the moment. So keep tuned. We are hoping we can keep improving what we have so far. So now let's get back to the second order query experience that I promised. So even though we've disabled the query interface for running second order, we pre-prepared a results here, which resembles what you would want to do. So if you have run the data package, the results are already there. So please do that so that you can follow along. So now I'm going to switch to our environment. To do that, actually, I have to hack it a little bit because this current environment everybody has is lacking a fundamental feature that we are implementing at the moment. So let me get to our administrative backend. So this is really be warned. This is dangerous stuff here. So I've got a lot of admin, and I can probably see how many people are running right now following with us. Sorry about that. And this is my personal pre-prepared server, which has more power than those you have access right now. Let's see if I get in there. Okay, takes a little while because yeah, it's a heavy weight. So this part of demo, unfortunately, you guys cannot follow, but you guys can catch up in the second half. So this notebook currently runs. I have to use a much more powerful computational engine to run this. Which as you can see here, this is the remote kernel. These are how you use notebook interface to connect to external computing resources outside of the environment. The idea that if you have a powerful cluster of the computer in your own local execution, or you have some means that you're running on the cloud, you can bring them into our environment. So in this environment, you have access to the output that you saw previously, the query results, the package results, but you can run those results connected with the remote computing engine. So that's the idea. So let me see if it's running. Yeah, it's running. So to show you it's really actually running, let me try to log into our actual backend that's powering the whole distributed query. That's in it's actually running on a different cloud, which is Azure. So this is another showcase of our platform is actually cloud vendor agnostic. So our notebook everything runs in AWS, which is Amazon. But this particular Spark cluster is running on Azure. So let me see if I can log in here. So this is being a core sort of goal of CADRE's development is we want to be open source, but we also don't want to be, pigeonholed to a specific technology and vendor. So we try to use as much open source resources that are available in the community. In this case, Microsoft, they're not here, I guess I speak about. Microsoft recently really pushed us to use USQL, which is their proprietary distributed query system. But we decided to focus on, in this case, Spark, which is an Apache maintained system. I think if you're familiar to distributed data analysis, yeah, unfortunately, I should manage to cannot type and talk at the same time. I guess I'm missing the this IE login already. Okay, there we go. Oh, I have to go to the sign in again. Oh yeah, that's fine. Okay, cool. So we're using a database cluster at the back end, which actually consists of 16 node cluster that's trying to pass this the 0.1 billion records that you build. You can see here, it's actually running. So it's actually running 9 nodes. As you can see, when we run, it will scale up since they're dynamic scaling clusters. So if I go back to the notebook environment, which is on the separate page, I guess. That's here. Oh, it's here. Okay, it's finished running. Okay, that's good. So as you can see here, I've mounted my remote system to the notebook, and these are DBFS. If you know distributed computing, these are distributed file system that's running on my Spark cluster. So I'm going to only run a few things here, so it's great running, because these data are huge. Because we're reading billions of edges, even with powerful machines like that. It takes a lot. What you're trying to accomplish here is we're going to run the query, second query, using this cluster, produce a data set that on the subset. So unfortunately, even with this power, I cannot do what you asked me to do fully. So he asked me to give him all these second order indirect citations of Web of Science. I delivered that using IU supercomputer and crashing it in the process, by the way. And so he now has that result. But for today's, I'm going to do a subset of that, which is the direct citation and indirect citation of the scientometric and scientometric data set we just saw earlier today. So it's still running, so you can see it takes a long time. Let's just check. I think the cluster should now be scaling up. Okay, so it's not stretched up enough yet, so it's still stuck in 9. Well, I'll just quickly explain the rest of this code. What I basically did is get the query results that everybody gets from the interface. I matched that with this huge edge list now, a whole multi-academic graph using Spark cluster in a distributed way, and extracted all citations up to first, second order. So some of the code are, you don't have to understand them. As you can see, it's still in nature a relational operation, because I'm doing joins here. So this is a distributed relational query. In the interface, you saw single node graph query. So we are working on distributed graph query. So we're hoping by combining the graph query and distributed power, we'll achieve even better performance. Wow, this is taking quite a long time today. I'm not sure how long we can wait for that. There's some issues here as well. Okay, finally finished. So, I don't know, 5 minutes. So it's actually not that bad considering the size of that data we're handling. So we just loaded the whole data set, which is, in this case, 800 million pages. This is all the journals in MAG, actually. So I'm not going to run the rest, because each of them will take that long. But in the end, I will produce a data set and save it back to our platform so that you can access. So that's, in principle, how collaboration on this platform works. So Yibu asks for more scalable data analysis. So assuming I am his collaborator, I build this solution using a remote cluster, solve the problem for him, I deliver the data back to his environment. So that's the idea. And if you run the package of ISSI dataset, it's already delivered to your environment. So let's now go back to the more manageable size, which is the query results only now of Scientometrics magazines. Just to prove it's, let me see. Still running. I'll keep running this. If we have time, we can come back here. But we'll just forget about it in the meantime. So to follow along now, let's go back to the demo 4, which is actually one you can follow with me. So I'm assuming now you have got this delivered query results using distributed package. Now the simple code that Yibu showed you earlier can actually work. Although he sort of emphasized his code is very simple, doesn't scale, but once you combine it with a scalable query, you can achieve a lot of things. That's how I think a common sort of collaboration model we foresee in the future, where researchers with different expertise can collaborate. So here again, I'm reading the same query result you guys saw earlier today. And now I'm reading from the delivered second order results that I just used a powerful cluster to achieve. So it's still pretty big, as you can see. It has more than close to actually 100,000 edges. Because these now, according to what Yibu wanted, is a triplets: a photo paper, citing paper, and living notes. So so these, I'm actually reading some of Yibu's code. You probably recognize his code here. So I didn't change much here. And so you can do some analysis that Yibu was trying to do. I think he probably has much better. You can plot PDF with citations, right? You can plot the CCDFs, things like that. And you probably recognize this piece because he spent all the time on this code. This is exact code that he showed you, which will take forever to run the whole data set. But now, since our query has filtered into a target data set that you're interested in, now it's actually runnable. So it takes actually a couple seconds to run. That's sort of the way I see how the query builder and scalable engine can combine with more focused, research. Of course, if you're like you want all of the second order citations, you will have to you will either work with me or learn PySpark yourself and have a very powerful cluster to do this all of the papers in Web of Science. So just to illustrate that this actually builds what he's looking for, I'm just going to pick a random paper, and you can see, so that's the eagle citation network of a particular paper. It's a random paper I picked. I think it's so that's basically my demo. Some of the parts are not followable right now. It's real point is to showcase the flexibility of the environment, how we can combine external resources with our data environment. And in the future, we hope this combination can really bring the power and the flexibility that our user seeks. So I'll quickly wrap up because we are running close to the end here. So this big part of CADRE is really reproducibility. So I just demoed you a very complicated pipeline using quite sophisticated technology behind it. How can we reproduce that? Right, that's very tricky now. Getting all the things involved. So the fact is, reproducibility is not always going to be a given thing. And it's having taken more and more, basically, time consumed our researchers trying to deliver their research results in a reproducible way. So our goal here as a CADRE Fellowship really is to help you facilitate these steps so that instead of wasting time recompiling the code, explaining to users the software how to set the parameters, we want to be painless. That's a big part of the research economy, the package system we're trying to deliver. And we also want to make it life easier for you to query these large data sets. And the real talent and real time that our researchers possess to really spend on doing real research, come up interesting hypotheses, do all kinds of new statistical models, applying, interpreting these results. I think for us, we are really a facilitator of this cycle. But as I mentioned, as these pipelines get more complicated as data grows, achieving the end goal, which is, I think, according to Stan and Victoria, empirical reproducibility is, the ideal situation, but right now, even computational reproducibility is a challenge, and that's what CADRE is trying to facilitate. Because without computational reproducibility, all the following higher level reproducibility is nowhere to begin with. So the current solution of delivering reproducible data, algorithm data, is very, primitive. So this is my own way of doing this. So I list my paper, I provide a GitHub link. So you go to my GitHub, you can download my code. If the data is small enough, I might have a copy of the data file there as well. If it is too big, well, you have to find a way to download it somehow. And in CADRE, we really hope we can solve the data part of the problem as well as the code part of the problem as a combination. So it's a very tough challenge we're facing, but luckily the industry has already a lot mature solutions. Machine learning, AI is in all the rage these days. These guys in the industry already face similar problems. Their pipelines are getting so complicated, the development teams having trouble basically talking with each other. So this is essentially a Google solution, what they call Kubeflow. We don't need all the sophisticated machine learning components of it, but a lot of technologies we borrowed in CADRE is inspired by some of the open source products, including Jupyter, Kubernetes, and Docker container technologies. So these are sort of core technologies driving the system you're currently using in our demo, and it's make it possible that we deliver this computation environment in a efficient and flexible way. So to wrap it up, just quickly point you to a live and real reproducible delivery that I have created for our own paper. So this is my main delivery message now. So this is to follow this demo. You just, I think there's a link in our GitHub repo. So I'm not going to go into it because of time, but you can see if you get a GitHub repo. I have a separate repository where you can reproduce this very complicated pipeline. So in this particular paper, we have 3 collaborators, each in different languages. I was using Python, one of our collaborators using R, that is Java for graph visualizations. All of them now working seamlessly together in a predefined environment. All you have to do is click this button. So try that out, and it will deliver a pre-prepared notebook environment that we've been using previously. This is Binder, by the way. This is not by our technology at the moment. It's hosted publicly by Binder.org. So we borrowed a lot of ideas from them, and our goal is really go one step beyond on top. What they did is, because if you're software pre-sales, not everybody's comfortable with playing with code in notebooks. Our real goal is to really make it a marketplace that everybody can click and run these packages, even without looking at the code. So to achieve that, we really need help out from our community. Our fellows, some of them are already pledged to submit packages that can clean the data, can detect author, disambiguate author IDs for you. The hope is that the user of these packages will not have to worry about the detailed algorithm if they are satisfied with the results. And then we can progress the field without constantly reinventing the wheel. So this is what we envision in the future, hopefully. So the hierarchy of the ecosystem. Our CADRE team only will build the core component, providing the environment, the query engines, and provide some of the APIs. On top of that, our users will use them to create their own packages, collaborating with each other. And as I promised earlier, we will open source everything that we implement in CADRE. So if you want to deploy slightly different versions of CADRE for your own data set, you will be able to do so using our codes for different purposes and data sets. So this is, I think, the conclusion. Before I think there is still a question and answer session before we have everything, but you've seen many important components today, including query interface, as a comments, notebooks, and some of the database implementations. So I also have keep in mind this is our proof of concept preliminary implementation at the moment. A lot of components are subject to update and improvement as we move along. So for that, we really ask for your feedback and grow with us together. And hopefully, we will forge a platform that's going to work for a lot of people and facilitate their research with these bibliographic data sets. So I think that's all I have to say for the demo. I think our team is here, and the fellows. If any of you have questions, I think this is the right time to ask.
What about the licensed data sets?
That's a very good question. So reproducibility currently, as it assumes, everybody will have access to the data. With licensed data sets, the most reasonable approach we envision will be reproducible by people with same access to data sets. I think this is a great opportunity that we have with CADRE, especially the BTAA joining us. Because previously, I think we tried to reproduce Web of Science results with other institutions who has similar data sets, but not exact same. And there are certain legal barriers in terms of how can you share results based on slightly different data agreements. Now, with everybody joining as a community, kindly by Web of Science group, I think now we have much better, easier time, at least sharing results within ourselves. I think similar story can be said about, big scalable pipeline as well, because sometimes it's irreproducible if some data pipeline takes a huge cluster, for example. Only those that accept that will be able to run it. So that's another concern that we have, and unfortunately, we don't have the means to support free computing, credits in the cloud. But we hope by bringing external computing powers, like in this case, thermal kernels, at least you're calling from your same institution who have access to the same cluster, will be able to reproduce the same set. So it's always our hope that we can further break down these barriers. But really always the challenge is same. We are keep working on it.
Where the results are shared. You have access to the query information. You have access to the results on all of it. Will the query report send it?
No, it's actually finished running. So if you just come back to the Databricks cluster I started earlier, I think the cluster now should grow into 9 sites. They're constantly resizing right now. So, so depending on the level. Yeah, okay, yeah, because I've been running it. So this is the 4 sites of network that I have provisioned for this challenge. You can actually see what's going on there as well. Go to the Sparky, if you're familiar with it. We have finished some pretty big tasks where you have, 65 threads running in parallel, trying to parse the data. So feel free to ask any questions, like access, how to join us. I think the rest of the presentation is just upcoming events. So if you would like to be updated with our follow-up events, join our commission channel about Twitter. You can always get the code that we developed today in the Git repo. We will actually improve it, because right now I think we are lacking a lot of instructions in the slides as well. So we will keep it always there, because we also plan to accumulate a set of educational material on how to use CADRE. So that's how we're recording this as well. All right, if there are no more questions, I'll just call it a day. Thank you everybody for coming, joining us, and hope to see you in the future CADRE events. I have to stop recording.